Okay, hello class. Welcome to the last lesson of quadratics, but it will take us some time to practice still. Is modeling the skills, and so the skill of modeling a quadratic, so creating your own function. So the question is, how many points do we actually need to create an equation? And the answer to that is like just enough so that you can draw it. If you can't draw it, then you probably need more points. And so if you have two zeros and a point, you can draw it. So like the vertex, you're still going to figure it out, but it's going to go symmetrically through, and somewhere it's going to be above. You might have to figure out where that is, but you can at least draw the equation. If you only had the two zeros, like you wouldn't know how high up it goes. But once you have the point, it tells you the shape to take. Or you can have a vertex and a point. So if you think about that, as long as you know which one's the vertex, you can like use symmetry to figure out the other one. And so if that guy's the vertex, then this point would have to go over here as well. And the only way to draw a quadratic is like this. So it's just enough to draw it. And so that's the information you're going to have. If you have a vertex and 1 point, you should be able to get it. If you have two zeros and 1 point, you should be able to get the equation. So what we're learning is creating like the appropriate algebraic representation using a quadratic model. And we saw one of these when we did the business marketing question. We're going to see a couple more, and we saw some of these questions already when we talked about the problems in general. And so now we're going to actually look at like specifically how to set up those equations. So developing a plan is still important. What do we know? Like sometimes a lot just by giving the equation, but it takes some skill or some like practice to get even what we know. And then what do we need to know is sometimes given after we create the equation. And how we get there is by creating the equation and then using a point. And then using the vertex and a point, or by choosing appropriate values for x and y. So what are you going to let x represent? And so here's the first question here. We've got a bridge and a parabolic arch. So this is the question we asked before. What do we know? What do we need to know? How we're going to get there? So if we actually drew the bridge 0 to 42, so they're 42 meters apart, the vertex would be right in the middle. It's the height of 26, but the x value 21, we actually know that given in the question. It's inferred in the question, like, so we have to dig a little bit deeper. What do we need to know is create the equation. And how we're going to get there is by using these zeros and the point, or using the vertex and the point, and one of the points, we can solve for the a value. So this is the equation we have to create. Using factored form, you can set it up. So we have our zeros of 0 and 42. So the first one, like, you're going to see it this way. This is still factored form. It's just if x minus 0, you just see it like this. Then what you're going to sub in is the vertex, and that'll help find for y. So the x value of the vertex goes in everywhere you see x, and the y value of the vertex replaces f of x. And then it's just a matter of like calculating the negative 441 and then dividing by both sides by negative 441. Using vertex form, we can go right to the vertex. Just finish it by writing out the equation. So the goal is not to find the a value, it's to find the equation. And so by using vertex form, we could use one of the zeros to solve for the a value. So we're just going to use, it doesn't really matter, 42, 0, or 0, 0, it doesn't really matter, use 0, 0. So that gives you 441 times a plus 26, which you might want to write 441a plus 26, and later on we do it that way. Subtract 26 from both sides, divide by 441, we get an a value, and the equation looks a little different, but it's the same thing algebraically. This is factored form, this is vertex form. So either one you could use because you've got both zeros and the vertex. Often you could only do one of these because you wouldn't be given all those key features, both zeros and the vertex. Vlad Guerrero Jr., last time we did this I had Jose Bautista, so I just updated it. But Vlad Guerrero Jr., so this is the home run one at Tropicana Field. So we're just going to kind of look at creating an equation for this. So it tells in the question, you can flip back to the question if you want to. but it tells in the question that like the ball is hit from a height of 3.5, so I'd probably call that my y-intercept. It gives you the maximum height, and then it asks you really where, it doesn't really tell you, well, I guess you know where it hits the ground, so you do have this point as well, but you just don't know if it's going to be over 15 at 328 or not. And so we have to actually create an equation so that we can test that point of 328. The x value in this case is just the horizontal distance. That's kind of like a little bit easier to set up than other ones, but that's the horizontal distance. And so we've got vertex form. If we sub in the y-intercept, we can like then use like some algebra to solve for a, and then we get an a value that looks a little funny, but it's just like opening down, and so make sure like it does open down for our equation. Even though it's like kind of like a really awkward a value, it still kind of works, and so it's just from the y-intercept, that's just what we got. And so now the question is, if you subbed in 328, is it over the wall? Is it over 15? Some people would get stuck on what to do there, like where do I put the 15, where do I put the 328? And what I would do is I'd just sub in the independent variables, see what the dependent variable is. So if we sub in 328, which is where the home run wall is, not where the ball hits the ground. Sorry if I said that before. It was 344 is when the ball hits the ground. But that doesn't necessarily mean that it's going to clear the wall. It could hit the middle of the wall. It all depends on where it is. But if we sub it in, we actually get, after doing the bed mass really, we get 18.84, which is actually over the wall. The wall is 15. Okay. And the last one, so we got the Mr. Bookaboom one again. So doing the backyard pool. Deck is uniform width all the way around, so it looks kind of like this. You got 16 by 12 is the yard, and then you've got X all the way around. And so then what you're actually given in the question is that the dimensions of the pool are 12 minus 2x and 16 minus 2x. That's not, like, that takes a little bit of setup, but that's actually given in the question, that the dimensions of the pool are that. So it lets you set up the equation for the area. So the question's asking you, like, what are the dimensions if the area was like 96, which is half the dimensions of 12 by 16. Now we have a situation where we have factored forms, so we could get zeros, but that's not actually helpful. Like, we want to find out when is it equal to 96. And so what we need to do is actually expand it out and then get to a situation where you have 0 equals. Combine like terms and then find your zeros. I wouldn't jump to the quadratic formula right away. Actually notice that a 4 will come out. And then it actually factors nicely, x minus 12, x minus 2. But in like a real world situation, like rarely factors nicely, so you might have to use a quadratic formula. And so the answers are 12 and 2, but the only one that actually works is 2, because 12 just doesn't make sense. Like, this whole thing is 12, so we can't take away 12 on both sides. And so then the pool is, if this is 2, then you realize that this has to be 16 minus 4, which is 12, and 12 minus 4, which is 8. Okay, and that's it.